All right, you guys, welcome to week 1 of online chemistry. So today what we're going to be talking about in this week in general is we're going to be looking at chemical reactions, types of reactions, and balancing those reactions. A lot of this should be familiar to you guys because I know that a lot of you guys have actually learned this in a previous class. But let's go ahead and start off with the basics of what a chemical reaction is. A chemical reaction is a process that involves the rearrangement of molecular or ionic structures. So as you can see on the screen in front of you is we have a reaction that's occurring. We have some molecules of hydrogen, we have some molecules of oxygen, and what they are doing is that they are reacting and they are creating something completely new. And if you look at that new molecule, hopefully you recognize that they are creating some water molecules. So let's go ahead and identify the different parts of a reaction. The reactants are the starting substances of the chemical reaction that undergo the chemical change. When you're looking at a chemical reaction, they're usually found on the left side of the reaction arrow. So let's go ahead and take a look at this chemical reaction that we have right here. So in this chemical reaction written out, this is actually the same chemical reaction from the previous page, but you can see that it's written out with molecules instead of using a diagram. So if we were to identify the reactants in this example, what we would see is that they are actually the hydrogen and oxygen. The hydrogen and oxygen are the two things that are reacting together. On the other hand, our products are the molecules or ionic substances that are produced during the chemical change. These are found to the right of the arrow or on the right side of the reaction. And those are our two water molecules that are being produced. Now, in order to fully label our reaction, we need to also identify the states of matter. It's important to note that the states of matter of the reactants and products should be labeled if possible. And one of the reasons why we want to make sure that we label them is that depending on what state of matter a product or reactant actually is, it actually changes the chemical reaction and it actually changes how they react. So where possible, it is important to make sure that we identify what state of matter they are in. And we identify this by putting subscripts after each substances. And there are 4 types of subscripts that you should be familiar with. The first one is a S for solid. Then we have an L for liquid. We have a G for gas. And an AQ, which means aqueous, and that means that it's dissolved in water. So if we were to apply subscripts to our previous reaction, what we see is that we have some hydrogen gas and some oxygen gas, and they react to form water, which ends up being a liquid. Now, when we're balancing reactions, we balance reactions because we want to make sure that a reaction is obeying what's called the law of the conservation of matter. This is something that we've actually already talked about in this class. It basically says that matter cannot be created or destroyed. So whatever we start off with has to be what we end up with at the end. So the type and the number of individual atoms must be the same in the product and the reactant. We can't change the atoms. We can't have sulfur and oxygen on one side and change it into nitrogen and fluorine on the other. They have to be the same things. And they also have to be the same number. So however many we have on one side, we must have on the other. If you were to add up the individual masses of each substance, the masses that we find on the periodic table, the masses should be the same on each side. For example, if you were to add up the mass of our 2 hydrogens and some oxygen, you should end up having the same mass as what's produced in the 2 water molecules. Balancing a chemical reaction. So there are a couple steps. The first step is to take inventory of each type of atom. And I usually do this by first making a list under the arrow of each atom that appears on both sides of the reaction. Then I'm going to identify the number of each atoms in the reactants and then on the products, and I'm going to write those on either side. Then, in order to balance the reaction, I need to add coefficients. Coefficients are the only things that you can add in order to change the number. So coefficients are whole numbers that are placed in front of a molecule or ionic compound to make the number of each atom to be the same in the product or the reactants. So we add these coefficients and then we can multiply them by that number, and then we can change how many atoms we have on the product or the reactant side so that In the end, they will equal each other. After you do this, you want to make sure that you take inventory again, and you want to double check that the number and type of atoms are the same on each side. Now, these 3 steps might seem fairly easy, but it is important to note that in some reactions, you might need to do this process a couple different times. So even though some reactions are pretty straightforward, sometimes this step needs to be done 3 or 4 times in order to make sure that the reaction is balanced completely. So what we're going to do is we're going to go ahead and we're going to take a look at 4 different examples, and each one of these examples actually shows us something slightly different. So let's go ahead and switch screens. So I still have the slide right up here, but let's go ahead and start solving some of these problems. So let's go ahead and start with number 1. So number 1, what we have is we have N2O5, and it produces nitrogen and oxygen. Now, as I said in my steps, the first thing I'm going to do is I'm going to take inventory. So what I see is that on both sides, the only 2 atoms that are found are nitrogen and oxygen. So I'm going to go ahead and I'm going to count out how many of these 2 atoms do I have on each side. So nitrogen, I have 2, and oxygen, as you guys can see, I have 5. On the other side, what I have is nitrogen, I have 2, and oxygen, I have 2. So what we see is that the number of nitrogen atoms are actually already balanced. So what we need to do is we need to pay attention to the number of oxygen atoms. And we see that we have 5 on one side and 2 on the other. And somehow we need to make this amount equal. So what you need to think of is what is your lowest common denominator for 5 and 2? Hopefully you guys see that the lowest common denominator is 10. So what I'm going to do is, in order to make 10 on the reactant side, I'm going to go ahead and I'm going to add a 2 in front of here, and that changes that number to 10. But I also want to go back, and what I want to see is that it actually also changes the number of nitrogen. So I do need to change the number of nitrogen to 4 to represent that. Now let's go ahead and finish my oxygen, which means that over here I need to put 5, and that changes the total number of oxygen to 10. And going back up to the top, if I want to change the number of nitrogen, what I'm going to do is I'm going to go ahead and put a 2 in front of here, and I'm going to see that it ends up being 4. So what I have on each side is that I have 4 nitrogen atoms on each side and 10 oxygen atoms on each side. If I were to talk about my my coefficients, see that my coefficients are 2, 2, and 5. So let's go ahead and move on to the next one, number 2. I have C5, H12 plus oxygen, and it yields CO2 and water, H2O. So let's go ahead and take inventory of what atoms I have. I have carbon, hydrogen, and oxygen. So let's go ahead and add up the amount on each side. So on this side, I have 5 carbon, 12 hydrogen, and 2 oxygen. On this side, I have 1 carbon, 2 hydrogen, but notice that my oxygen are in 2 different locations. So I do need to add those together, and you see that I have a total of 3 oxygen. Now, if you have a substance that's in 2 different locations in the product or the reactant, like we do with oxygen in the product side, go ahead and balance that one last. Hopefully in the end, it will balance out. So if I look at this, what I see is I'm going to go ahead and add a 5 in front of here to balance out my number of carbon, but that does change my number of oxygen. So let's go ahead and recalculate my number of oxygen. I have 10 plus the 1 over here, so that's going to be 11. Let's go ahead and balance out my number of hydrogen. So in order to balance out my number of hydrogen, I need to be able to put a 6 in front of here because that will change my hydrogen to 12, but that also just changed my number of oxygen. So I still have 10 in my carbon dioxide plus 6 in water, so now I have 16. So in order to balance out my oxygen now on my reactant side, I'm going to go ahead and put an 8 in front of here, and that gives me 16. So you see that we have the same amount on each side. So again, my number of coefficients, even though there's no coefficient over here, we do have a coefficient of 1, but we don't put it because that would be redundant. And we have 8, 5, and 6. So those are my coefficients that are added to that reaction to balance it. Number 3. Number 3 looks very similar to number 2, but there is a significant difference that we will see as we start balancing it. So it does follow a very similar format, but there is one big difference. So let's go ahead and get started, and we'll see that we have carbon, hydrogen, and oxygen as we did in the previous one. We have 8. That really messy, this is actually at 18. It got a little messy. And we have 2. Over here we have 1, 2, and 3 oxygen. So let's go ahead and start with my carbon. So in order to balance my carbon, I'm going to put an 8 in front of here. That changes that to 8. But that also changes my number of oxygen, and that changes my number of oxygen. So we have 8 times 2, which is 16, plus 1, which is 17. Let's go ahead and work with my number of hydrogen. So my number of hydrogen, in order to make this equal 18, I'm going to go ahead and put a 9 in front of here. That changes that to be 18. And then I have 16 plus 9, which is 25. Now this is where it becomes a little bit challenging, because what you see is if you look at oxygen and you look at the numbers that you have on each side, you have 2 and you have 25. So what I'm going to do is I'm going to do a shortcut. And I'm going to say, what do I need to multiply my oxygen by to make it equal 25? And I actually have to multiply it by a fraction. I actually have to multiply it by 12 halves. Because if I multiply 12 halves by the 2, you see that we get 25. Now, you might think, well, can we put a half in front of there? And the answer is no. But one of the things that we can do in order to get rid of that half is to multiply the entire reaction now by 2. So I'm going to go ahead and I'm going to put a 2 in front of here. I'm going to multiply this by 2, and I do get 25. I'm going to multiply this by 2, and I get 16. And I'm going to multiply this by 2, and I get 18. So my coefficients are 2, 25, 16, and 18. And if you recalculated that, you would see that we do have the same number of atoms on each side. So that's kind of a tricky one, and you will usually see it in these type of combustion reactions where your carbon is an even number. So let's go ahead and move on to number 4. So we're going to scroll down here just a little bit. And we have number 4. Number 4 is, number 4 looks like it could be really complicated, but there actually is a shortcut that we're going to be taking for this one. So I have NH4, and I have 3, and there's nitrogen, plus CrO4, that's a polyatomic ion, and then we have a NH4 2 CrO4 plus Cr3N4. All right. So in this one, you might think, oh my gosh, that is a ton of atoms to keep track of. But there is a shortcut that we can do. And the shortcut has to do with the idea that if you have a polyatomic ion like we do right here, so we have ammonium and we have chromate, what you're going to do is you're going to keep those together as a unit, because as you can see, they don't break apart. So we're not going to break them apart because they don't get broken apart in this balanced chemical reaction. So when I write down what I need to balance, I'm going to go ahead and I'm going to say I need to balance ammonia by itself. I need to balance chromate by itself. I also need to balance nitrogen and chromium. So I don't have to break down those polyatomic ions if they don't get broken up in the chemical reaction. So if I identify how many I have 3. Let's see, I have 2, I have 1, and I have 1. Over here, I have 2, I have 1, I have 4, and I have 3. So let's go ahead and start balancing our reaction. So looking at our ammonium, we see that we have 3 and 2. So we need to think of what is our lowest common denominator, and the answer is 6. So that means I'm going to multiply this side in order to balance it out by 2. And that's going to change this to 6, and that's going to change my nitrogen to 2. And I'm going to balance this side by adding a 3. So that's going to make this 6, and that's going to make this 3. So now we have our chromate. And we need to do the same thing. So we have 2 and 3. So our lowest common multiple for that is going to be 6. So in order to get 6, I'm going to multiply this side by 3, and that's going to make this 6, but that's also going to make my chromate 3. And then over here, I need to change this 3. I'm going to go ahead and erase that, and I'm going to change this to 6. Now that does change my ammonium to 12, but that changes my chromate to 6. So I'm going to come back to ammonium. I'm going to keep working down my list. And let's go ahead and go over here to nitrogen. So we see that we have 2 and 4. So that means I need to double my nitrogen on my reactant side. So again, I'm going to erase that. And instead of a 2, I'm going to replace that with a 4. Now that balances out my number of nitrogen to be 4. And what we see is that actually automatically balanced out my amount of ammonium to be 12. So it actually ended up balancing itself out on its own. So what we see is that my coefficients are 4, 3, 6, and again, that unnecessary 1. Now what we want to do is we want to talk a little bit about how do we actually read these chemical reactions into words. So if I were to read this, am I going to say like 2C8H18? No, that kind of sounds weird. So we're going to learn how to read these in words. So in a chemical reaction, the coefficients, those numbers that we put in front, can be read as a number of molecules or the number of moles of that substance. We also want to, if it says the state, we also want to make sure that we identify when we're reading the substance what state of matter it's in. So we're going to look at our example that we had at the beginning, and we're going to read this in words to kind of say what this chemical reaction is. So there are 2 ways that you can read this. You can either say 2 molecules of hydrogen gas react with 1 molecule of oxygen gas to produce 2 molecules of liquid water. So that's one way. The other way that you could read this chemical reaction is by saying 2 moles. So we could also say 2 moles of hydrogen gas react with 1 mole of oxygen to produce 2 moles of liquid water. Notice that I cannot say atoms because those do not represent atoms. I have to use either molecules or moles. So those are the only 2 words that I can use to read this chemical reaction. And this is going to become really important next week when we start learning about stoichiometry. The last thing that we're going to be talking about is, or I'm going to be talking about, is types of reactions. And there are 5 types of reactions that we're going to be going over. So I have them listed here, but let's go ahead and go to the next slides because I go into each one of these in more details. So let's start off with the first one. And the first one is synthesis or formation. And you will see these, this one named either way. People use these terms back and forth. So in a synthesis or formation reaction, the reaction where multiple reactants combine and they form one product. If we were to think of a general formula, I would say A plus B produces AB. So we have 2 different substances and they yield to form one single product. In an example, we have 2 moles of magnesium plus oxygen, and they produce 2 moles of magnesium oxide. That is a synthesis reaction. Notice that 2 separate things are forming one compound. And we've actually done this, and I have a short video that you guys can watch later, but a short video here to kind of show you guys this reaction.
If we have a piece of magnesium, we can actually, there's oxygen all around this all the time. There's oxygen right now. But the magnesium is not going to react with it until we kind of give it a little nudge. So what I'm going to do is I'm going to put it in the fire. Now you're safe at home or in class watching this on the video screen, so you're probably going to be safe. But I'm not going to look at that because I'll burn out my retinas. And the person who is holding the video camera also is, oh my, I glanced at it for just a second. It's a this particular synthesis reaction is an extremely exothermic reaction, gives off a lot of heat. Oh my. All right, it's done. You can zoom in now. We got so there's the magnesium that is left that did not burn. And down here you can see this, we might just call it ash because it's crumbly stuff. It'll, it's almost like chalk. That is the magnesium oxide. That's what
All right, so just very quickly, you guys saw in that video what he had a piece of magnesium metal and he reacted it with the oxygen air. the oxygen in the air, and in order to do that, he had to heat it up. So heat was required in order for those two things to react, and he was able to produce magnesium oxide. I want to also note that this can also be described as a combustion reaction as well, and we'll see in a couple slides what a combustion reaction is. Now, the exact opposite of a formation reaction is a decomposition reaction. So this is a reaction in which a compound breaks down into two or more simpler substances. So think of the exact opposite. So instead of having A plus B, we have AB, and it breaks up into its simpler components. So we have A and B. So reaction is this substance, and we have what's called sodium azide, and it breaks apart into sodium and nitrogen. And so right here in this little video, we have someone that describes actually what this reaction is, because it actually has a pretty interesting real-world application. Oops, let me go back. There you go.
Beverage. What's decomposition then? It's when we're taking a compound and breaking it down. So here's an example. If we take sodium azide and break it down into sodium metal and nitrogen gas, that'd be a decomposition reaction. So if we have one reactant and two products, it's a good idea that this is probably a decomposition reaction. Where's an example of this actual reaction? Well, this was used in early airbags. And so what you can do is you can put some sodium azide inside the bag right here. It's totally stable, but if you add a little bit of heat to it, so there's an igniter inside there, it's going to quickly break into sodium and nitrogen gas. And that nitrogen gas is going to fill up the bag really quickly.
All right, so that's our decomposition. So let's go ahead and take a look at what's called a single replacement reaction. So a single replacement reaction occurs when one element replaces an element in a compound. So what might that look like is we have this general formula. We have A plus B, and then we have this single compound C. And what happens is that C will replace B in that compound, and we will produce B plus A and C. So here I have this example. We have zinc, and we have lead 2 nitrate, and it produces lead and zinc nitrate. So we actually have an example of this in this video where he is actually combining these two things, and you will see that we will produce some lead and zinc nitrate.
It's very simple. So here we have some normal test tube and some lead nitrate solution. Simply pour it in, and to get it started, just drop the piece in. So here's the piece of zinc, and we're just going to drop it right in. You don't have to mix it. The reaction should start right away, and it just takes a little bit of time. So if you look closely here, the reaction is already occurring. Look at this piece of zinc. It was silvery, but now it's really dark. And what's happening is the lead is forming as a solid, and the zinc is going into the solution. That's harder to see, but you can see the lead is forming as a solid. I'm just going to shake it around. The solid lead is that dark black stuff, and it is kind of flaking off. Some people say like, oh, it's growing or some fur grew on it, but no, that's the lead. And you can see that it is quite dark, and you can put a scoop.
All right, so that's that reaction. So we see that there was lead that was forming, so that black stuff that was kind of growing on that piece of zinc, that was actually lead that was forming on that zinc, and the zinc was actually going into solution, and it was forming zinc nitrate in solution. Now, a double replacement reaction is very similar to a single, but what we have is we have two compounds, they react, and the positive ions, the cations, and the negative ions of the two reactants switch, and they form two new compounds. So again, our general formula, if we have AB plus CD, what we end up having is AD plus CB. So they almost like they switch partners. And what we're going to see in this video is that we're going to see sodium sulfide, and it reacts with copper 2 sulfate, and it produces sodium sulfate and copper sulfide. Oops, let me go back again. There you go.
First, I prepared a copper sulfate solution by dissolving a small quantity of copper sulfate, probably about 0.5 grams, into about 5 milliliters of water. I have here an approximately 0.1 molar solution of sodium sulfide in water. I will now drip the sodium sulfide solution slowly into the test tube. You can immediately see a dark precipitate of copper sulfide. Right now, the copper sulfide is concentrated near the top. I will now swirl the test tube to move the sodium sulfide lower down. As it moves down, more copper sulfide is precipitated.
All right, and so that is our single replacement reaction. Now we have one last reaction to talk about, and that's probably the most exciting. It is a combustion reaction. So in a combustion reaction, what happens is that a substance reacts with oxygen gas and it releases energy in the form of light and heat. So very classic of what you would think a combustion reaction would be. Lots of light, lots of heat is produced, and it has to react with oxygen. So you have A plus oxygen, and it might form something like A and O, like we saw in the synthesis reaction, but it also could produce something else. It could also produce something like water and carbon dioxide. So it could produce several different things. So in this reaction, in this video, what we're going to see is we're actually going to see ethanol react with oxygen, and it can produce carbon dioxide and water. And in this video, she actually does a really good job of explaining kind of what's happening. Let's go back. There you go.
All right, the demonstration we're going to do today is to show the combustion of ethanol, a highly flammable liquid. Okay, so we're going to take our ethanol. We're going to pour all our ethanol into this large bottle here, and then we're going to shake the bottle around. What we're doing here is we're making ethanol vapour. With a really good shake. Alright, and there should be now very, very little left in. So, now at arm's length, using a taper, I'm going to light the taper and light the vapour inside the bottle. Now you'll remember that bottle's empty, no liquid in it at the start of the practical. If I tip this up now, you can see, we've made a liquid, and that liquid is essentially just water. There's a little bit of contamination in there.
So the last thing that I want to talk about is just your to-do list for the week. So a couple different things. There is a homework assignment that is posted. It is balancing reactions and identifying types of reactions. So you want to make sure that you solve that homework on a separate sheet of paper, take a picture, and submit it on Google Classroom through the assignment. Please note that I will not grade homework that is emailed to me. Also, please make sure that you turn that in by Friday at midnight. There will be a mini multiple choice quiz check that will be available Thursday at 8 a.m. and you will have until Friday at midnight to finish that. It's multiple choice. It will automatically grade it. So when you see that, please make sure that you guys remind yourselves to take a look at that. My office hours for chemistry this week are going to be Wednesday at 1 o'clock and Friday at 10 a.m. So if you want to come to one of those office hours, the Meet ID and the password are there. I will also be posting these on Google Classroom. So if you have questions, make sure that you stop by my office hours on Zoom. If for some reason you can't make it to those office hours or you don't feel like doing Zoom, that's totally fine. But do make sure that you guys email me and shoot me questions and things like that so I can answer them as they come up. I want to make sure that I am answering as many questions as possible. So feel free to reach out. Just make sure you guys watch the videos, and I will hopefully see you guys on one of the Zooms coming up later this week. I hope you guys have a good start to your week, and hopefully I'll see you guys soon.